But what about beyond our solar system? Could life in all its complexity exist out there on a planet among the stars? For as long as we've had eyes to see and minds to wonder, we've marveled at the bright lights in the sky. But it was only on the eve of the 21st century that a handful of eccentric thinkers dared to gaze into the gloom between the stars, believing planets like our own world could be found there. Michel Mayor was one of them. In the 1990s, astronomer R. Paul Butler was another young radical who gambled his career on the hunt for exoplanets, planets orbiting stars other than our Sun. At the heart of the challenge was one fundamental problem. Even if there were exoplanets out there, scientists knew they'd be impossible to see directly because the brightness of the star would overwhelm the planet. To overcome this obstacle, astronomers developed an ingenious method of hunting exoplanets by stealth. Imagine the hammer is the planet, the athlete its star, and the chain between them their gravitational bond. The star pulls hard on the planet, but it's not all one way. The planet also pulls on the star. In fact, with every revolution, it's pulling it a little off balance. Using a prism-like instrument called a spectrograph, this wobble effect can be detected by observing changes in the color of the light emitted by the star, shifting towards blue as the star moves closer and red as it moves away. Measuring this oscillation allowed Queloz and Mayor to infer the existence of a planet, to calculate its mass, the distance from its star, and the duration of its orbit. On the 6th of October 1995, Mayor and Queloz announced their discovery. The first ever exoplanet, Bellerophon. Although they could not see it directly, its mass suggested it was a giant gas planet, similar to Jupiter. But the distance from its star and the period of its orbit seemed to defy the laws of our solar system. In our own solar system, giant gas planets exist only in the colder outer orbits, whereas Bellerophon appeared to be tucked in tight against the heat of its star, much closer even than Mercury is to our Sun.
Because it's so close to its star, it's really, really hot. It's probably something like of order 2,000 degrees centigrade, and there is no solid surface because it's a gas giant. So it's not a good place for life. It's not a place you'd want to visit.
Bellerophon was no second Earth. But its discovery had opened the window on a new vision of the universe, where anything is possible. In 1999, Professor of Astronomy David Charbonneau was just a young grad student at Harvard, trying to make his mark in the brand new field of planet hunting. What he encountered was a minefield. While artists had rushed to bring these new worlds to life, skeptics questioned the astronomers' interpretation of their data. Charbonneau relocated to Boulder, Colorado, to a small shed in a car park where a basic 4-inch telescope had been set up by fellow researcher Tim Brown. Where the wobble method allowed one to infer the mass of an orbiting exoplanet, Charbonneau was attempting to observe the planet's shape as it passed across its star, in the manner of a partial eclipse. The problem was, he knew the odds were stacked against him. Tipped off that another so-called hot Jupiter like Bellerophon had been detected by the wobble method, Charbonneau trained his telescope on star HD 209458 and waited, praying for a transit.
There had been about 10 hot Jupiters discovered at that point, so It seemed like if there really were planets, if we weren't being fooled, then sooner or later, one of these transits should occur. And right when we predicted, based on the wobble data, that a transit would occur, that's when we saw this event.
Charbonneau's transit method was a game changer, confirming the pioneering discoveries using the wobble method and silencing the skeptics. The new look universe was populating fast, inspiring an eager generation of young scientists to join the hunt. In 2009, scientists launched a formidable new weapon in the hunt for life beyond our solar system. The first dedicated planet-hunting telescope, Kepler. At the time, it was the world's largest digital camera, using an array of 95 megapixel sensors to detect the infinitesimal dimming of starlight caused by transiting planets. So powerful that if turned towards Earth, it could detect a single porch light turning off. More importantly, it was the first instrument capable of detecting rocky, Earth-sized planets.
The first 2 decades of exoplanets was kind of like postage stamp collecting. Kepler really changed that.
Kepler monitored a select region of our galaxy over a 4-year period by taking a snapshot every 30 minutes, like an epic time-lapse photograph.
And from that data, we identified over 4,000 periodic transit events that look like viable planets. And in fact, we have confirmed through other follow-up observations that over half of them are indeed bona fide planets.
Kepler delivered not only the first rocky exoplanets, it revealed brand new kinds of rocky planets, like Kepler 10b, our first encounter with what scientists would christen lava worlds.
These are rocky worlds, same kind of density as Earth, but they're orbiting so close to their star that the surface temperatures are in excess of that required to melt not just rock, but iron. So you've got an entire hemisphere, something the size of the Pacific Ocean, even larger, that is an ocean, but it's not an ocean of water, it's an ocean of molten rock.
Kepler was the first celestial census. Extrapolating the data from the surveyed region, it gave astronomers a catalogue of the exoplanet population. At least one planet for every star in the sky. And as many as a quarter of them Earth-sized and orbiting within the habitable zone. Kepler revolutionized the way we see the stars. Inspired by the success of Kepler, in 2013, NASA joined forces with MIT Lincoln Labs to develop an instrument that could deliver a more detailed survey of nearby Earth-like worlds. As the project advanced, MIT professor Sarah Seeger was named Deputy Science Director of the Transiting Exoplanet Survey Satellite, aka TESS.
TESS wants to find stars that are closer, right in our neighborhood, actually. The camera has a lens assembly of 7 lens elements that refracts starlight onto a detector, and together they make a giant strip. When you think of the sky as a sphere, from the bottom of one hemisphere all the way up to the pole. After 1 year of doing that, TESS will flip to the next hemisphere, and it will then do the same thing. And so over 2 years, TESS aims to study the entire sky.
By scanning nearby star systems, TESS aims to identify 50 Earth-sized exoplanet candidates for further investigation. But would finding a planet like our Earth also mean finding a star like our Sun? After the explosion of discoveries, a new question emerged. Could finding the right star be just as crucial as finding the right planet?
I think the biggest lie that I was told when I was in school was that the sun is an average star. The sun is not an average star. The sun is much bigger, much more luminous, much more massive than most stars. Most stars in the galaxy are about a quarter the size of the sun, a quarter the mass, and they only put out 1/1000th the energy.
These are small, cool stars, burning not yellow like our sun, but red. They're classified as M-type stars, or M dwarfs, but most people call them red dwarfs. One of Kepler's Earth-sized discoveries, planet Kepler 186f, was found to be orbiting such a star, 500 light-years from Earth. Because red dwarfs burn less hot than our sun, their habitable zone tends to be much closer in. But this closeness could spell disaster for life on the planet. When a planet is close to its star, the gravitational or tidal force becomes greater, and this can have the effect of locking the rotation of the planet, meaning one side is always lit by its star, while the other remains shrouded in darkness. As one is producing one hot side and one cold, by spinning so slowly, the planet may fail to generate an electromagnetic shield, which, like on Earth, protects the planet from radiation. But in 2015, Casting and other researchers found reason to hope for life on a tidally locked planet orbiting a red dwarf. Using sophisticated climate modeling, they proposed that if the planet had the right kind of atmosphere, then heat could be transferred from the light side to the dark, like a reverse cycle air conditioning system. Planet hunters embraced the discovery. If life could thrive on a planet around a red dwarf or M-type star, the odds of finding a second Earth were vastly improved. For 4 months at the beginning of 2016, the SEA telescope in Chile set its sights on the M-type star, Proxima Centauri. A mere 4.25 light-years from Earth, it's our nearest stellar neighbor. In a machine room deep beneath the telescope, light from the star was split by the HARPS spectrometer, an instrument so sensitive it picked up the feeblest of wobbles in the dwarf star, caused by a tiny Earth-sized planet, Proxima b. The discovery came as a revelation. The very closest alien star to Earth hosts a tidally locked Earth-like world. And calculations reveal that Proxima b is orbiting within the habitable zone.
It's an amazing triumph to discover a planet around our nearest star. Just think about that. For thousands of years, people have been wondering, are there any planets around other stars? And there is one around our very nearest star.
But what about its atmosphere? Could this planet sustain life? As the exoplanet gold rush gathered pace, planet hunting prospectors sought ever more refined methods of sifting their discoveries in an effort to give a future interstellar mission the best possible chance of targeting a world that might actually host life. Having identified a rich new vein of distant planets, the next crucial piece of the puzzle was yet to fall into place. How could a telescope be used to sample the atmosphere?
Looking at a planet's atmosphere far away is the best way we have to find signs of life on another world. Because the gases that life produces, here on Earth actually, imprint in our atmosphere in a very significant way. And so it's just amazing to think that on another world we can do the same.
If you were an alien astronomer studying the planets of the solar system, you would see that there's something very different about the third planet from the Sun. You would see that its atmosphere is full of oxygen, even though you would know that the oxygen couldn't possibly be there by geologic processes. There would be other gases, like methane, which also shouldn't be present, and yet there they are. And we think, as we're trying to do ourselves, when we look at other stars, conclude that life was the only possible explanation.
In 2000, David Charbonneau took control of the aging Hubble telescope, charged with a single but daunting objective: to make the first ever observation of an exoplanet's atmosphere. The transit method of exoplanet detection, which Charbonneau had pioneered himself, provided a clue for how to solve the puzzle. Planets orbiting closely to their stars make more frequent transits, and the larger the planet, the easier it is to detect. So Charbonneau turned the Hubble's gaze towards Osiris, a gas giant that transits every 3.5 days. Different atoms absorb different light frequencies in the electromagnetic spectrum and allow others to pass through, producing a signature in color. Charbonneau put his money on sodium, the telltale yellow glow of street lamps. After painstakingly probing the data, Charbonneau announced his discovery. The atmosphere around Osiris was indeed rich in sodium. However, this was no second Earth. Named after the Egyptian god of the dead, the gas giant Osiris doesn't even have a solid surface to land on, let alone a climate for life.
Of course, Earth-like planets are simply much smaller than gas giants, and so it's just much more difficult to detect them and to study their atmospheres.
It's the hurdle that has thwarted planet hunters from the outset. The blinding light of the stars completely overwhelms the smaller exoplanets. The first instrument to solve that problem will hold the key to the exoplanet revolution. The James Webb Space Telescope is designed to view the heavens like they've never been seen before, making the invisible visible. Its vast honeycomb-like dish of mirrors converges light into the eye of a state-of-the-art infrared camera that astrophysicist Pierre-Olivier Lagrange spent 20 years developing.
An object emits light in a given wavelength according to its temperature. For example, the sun emits in the visible range because it's very hot. If we take a human It's much cooler and will emit in a different wavelength, mid-infrared. And that's why with a so-called thermal or infrared camera, you can see people at night. We don't need lights. We see the heat emitted by a human in the mid-infrared.
The same is true of exoplanets. Observe them in the right wavelength, and they glow in the dark. But for the infrared vision to work, it relies on the truly innovative feature of this telescope. Inside the camera lies James Webb's secret weapon, a kind of mask called a coronagraph.
This form of mask is very unique. The light of the star arrives where it's opaque. On the other hand, if you have a small object next to it, like an exoplanet, well, the light will not have exactly the same path and will shine through. So, after that, we'll have the light of the exoplanet without the light of the star. So thanks to this coronagraphic method, we'll be able to get a direct image of the exoplanets.
The mask of the coronagraph intervenes between the overwhelming light of the star, like an eclipse, allowing the infrared light of the planet to shine through. Crucial in the hunt for Earth-like worlds, James Webb is ideally suited for detecting ozone.
But why ozone? Because there's no ozone without oxygen, and no oxygen without life. So we think it's really something that is a trace of life. And in the middle infrared, our telescopes can precisely detect this signature of ozone.
The James Webb promises to be the missing piece in the planet hunter's arsenal. With its breakthrough ability to view an Earth-like exoplanet directly and to study its atmosphere, the odds of identifying a destination for a future landing mission have never been better. Like most scientists, principal investigator of the Mars rover missions, Steve Squires, is a born explorer, a seeker of truth amidst the great unknown. In 1977, images of the Viking mission changed the course of Squires' life.
You know, it's not like today where pictures come down from Mars and bang, they're on the internet an hour later. There were only a few dozen people in the world who'd seen these. I didn't understand what I was looking at in the pictures. Nobody did. But then I would see in the pictures these little valleys that just looked like they had to have been carved by liquid water. And I was in that room for 4 hours, and I walked out of there knowing exactly what I wanted to do with the rest of my life.
In the early 2000s, Squires led NASA's Spirit and Opportunity rover missions to Mars, successfully landing the two robot geologists in a bid to uncover the hidden history of water on the Red Planet. Amid these groundbreaking triumphs, an even greater frontier beckons. The discovery of Earth-like worlds outside our solar system has transformed the way we see the universe and presents an irresistible challenge. Why not reach out even further and search for life on a planet among the stars? The closest star that hosts an Earth-sized planet, Proxima Centauri, is 4.3 light-years away, over 170,000 times further than Mars. Over the next 5 decades, Lee oversaw successful missions to Jupiter, Pluto, and to the comet Tempel-1. With Lee and other pioneers at the helm, humanity's exploration of the solar system has been so successful, we have a permanent office in space, the International Space Station. But as the new dawn of interstellar exploration lights the horizon, even the old sea dogs know it will be the greatest challenge that humankind has ever faced. And so the infinitely complex quest to search for life amongst the stars is reduced to just 4 problems: propulsion, navigation, communication, intelligence. Each one of them will demand a revolution. The goal of engineering missions to the stars confronts explorers with distances they've never even contemplated before. 1 light year is 5.8 trillion miles, which makes our nearest star over 24 trillion miles away. That's more than 1 billion round-the-world flights. According to the masters of solar system exploration, the greatest challenge is how to propel a spacecraft fast enough to travel light years within a lifetime. Only one chemical-powered spacecraft has ever made the leap beyond our solar system. In 2013, 36 years after its launch, Voyager 1 entered interstellar space at 10.5 miles per second. Fast enough to travel New York to LA in under 5 minutes. But at less than 0.0001% the speed of light, still painfully slow if you're aiming for the stars. As the push for interstellar exploration gathers pace, the workhorses of the old space race are put out to pasture. Monuments to a bygone era. But if not chemical rockets, what will deliver the seemingly impossible thrust and fuel efficiency required to journey to the stars within a lifetime? 3 potential propulsion solutions are being explored today: fusion, antimatter, and plasma.
Imagine we want to go to Proxima Centauri, the closest star to our solar system at 4.3 light years away. And imagine we want to get there in a few decades. If we use a conventional rocket, we can show that the amount of fuel we need is greater than the mass of the known universe. On the other hand, if we use a plasma thruster, we would only need tens or hundreds of kilograms of fuel. So then the mission becomes possible.
Physicist Stefan Mazouf is working at the cutting edge of electric propulsion. The Hall plasma thruster.
We start with a fuel in gas form. We will electrify it, and these electric particles, called ions, will be ejected at very, very, very high speed. It's the ejection of this material that will advance the spacecraft.
Since the 1970s, plasma thrusters have been used in satellites to make positioning adjustments while in orbit. Their principal advantage is efficiency, demanding just a tiny fraction of the mass of fuel required by chemical rockets. Plasma engines offer hope of achieving the speed required to reach the stars. Still holding them back is how long it would take to achieve that speed, dragging the total trip time into thousands of years. But in the shimmering upper atmosphere of our own planet lies the potential for a kind of propulsion until now only dreamt of in the realm of science fiction. In 1995, at the CERN Particle Collider in Switzerland, for the first time in human history, scientists succeeded in producing the most efficient source of energy achievable within the laws of physics: antimatter.
As any good Star Trek fan will know, right, on the Enterprise, that's what powered their warp drive. Of course, warp drive is science fiction drive. But if you think about antimatter, it's real. Just like normal matter is protons, electrons, there are antiprotons and anti-electrons. When matter and antimatter come in contact with each other, they annihilate. And it essentially is the perfect E = mc squared moment is released as energy. And therefore, it's the most efficient battery we can ever build, the most efficient battery that nature will allow us to have.
Antimatter is created naturally in space when cosmic rays collide with atoms in the Earth's atmosphere. Producing it at the CERN was a phenomenal scientific and engineering breakthrough that required accelerating particles to the speed of light and smashing it together. The challenge now is how to create enough of it to propel a spacecraft. The stars themselves suggest another possible solution to the propulsion problem. The energy released from hydrogen atoms fused together is what lights the sky across the universe. Since the 1950s, scientists have been developing fusion reactors to harness it. It's the holy grail of energy production. Tame the power of the sun and furnish humanity with an infinite supply of energy. But to get fusion going on Earth, you need to generate the heat of the sun. Upwards of 180 million degrees Fahrenheit. Modern reactors achieve fusion by other means, by heating plasma. The problem with this approach so far is that the energy required to reach that heat has been greater than the energy produced by fusion. No reactor on Earth yet has even reached break-even. But at Princeton Satellite Systems, a team of engineers is on a mission to solve that problem and to build a fusion reactor that can take us to the stars. In the realm of space exploration, the solar system is our neighborhood. Since visiting the moon in '69, we've dropped in on almost every body around the sun. In 2015, the New Horizons probe completed the first flyby of our most distant neighbor, Pluto. It took over 9 years to get there, but at every step of the way, the unmanned spacecraft was guided remotely from Earth. Sending directions to probes works for solar system exploration. But as we set our sights on the stars, the distances are so enormous, a new question emerges. How to navigate a journey of light years? Landed on Mars in 2012, Curiosity was the first spacecraft equipped with an autonomous navigation system. Given coordinates by mission control, the rover could image its surroundings and compute a safe path across the Martian landscape. But for an interstellar mission, there will be no relaying instructions. With any mission, communication is paramount. Most spacecraft do not return. Instead, they send their data back to Earth. Communication with every craft currently in space is conducted via the giant dishes of the Deep Space Network, each powerful enough to track a signal from Pluto, no stronger than a CB radio. When the New Horizons probe sent back pictures from Pluto via radio transmission, the signal was so weak, it took 15 months to downlink the images from a 12-hour flyby. But with the technology Abramson launched and tested in 2014, that download time could be reduced to just 1 day. Laser wavelengths are packed much more densely than sound waves, so they transmit more information per second and with a stronger signal. The greater bandwidth allows spacecraft to downlink multiple large packets of data simultaneously and in record time. 4.5 billion years ago, in the nursery of the heavens, a star was born. A giant cloud of dust and gas distended and ballooned until under the burden of its gravity, it collapsed upon itself, swirled into a disk, and forged a solar system from the dust. That star was our sun. Of the planets that were formed, only one that we know of gave rise to life. But could our sun, our solar system, our living Earth, have produced the only Genesis among the stars? Life is a miracle and an enigma, even to those who have spent their own lives trying to crack the code. NASA planetary scientist Chris McKay is one of them, part of a generation of scientists on a quest to find a second Genesis beyond Earth.
The search for life began with a lot of optimism, focused on Mars. Here was a planet that could have had a thick atmosphere, could have had water in the recent past, and in the popular literature at least, still had water. So the search for life on Mars really was thought to be easy. So then things basically went quiet in this search for life. And I think they were sparked again, not on Mars, but in the outer solar system.
The discovery of liquid water on the moons of Jupiter and Saturn, in the misty plumes of Enceladus, and the subterranean oceans of Europa and Ganymede, has opened a thrilling new chapter in the search for a second Genesis. The impact of identifying a separate origin of life on one of these worlds would extend far beyond our solar system. The renewed optimism in the search for life within our solar system emerged alongside a discovery that transformed the way we see the universe. In the early 2000s, NASA's Kepler telescope revealed that every star in the galaxy, just like our sun, is orbited by at least one planet. And up to a quarter of these so-called exoplanets are believed to be suitable for life. In the Milky Way alone, that means roughly 400 billion solar systems and 80 billion potentially habitable worlds. The odds of finding a second Genesis have never been better. Liquid water, carbon molecules, energy, minerals, and the secret formula that animates it all into a living cell. These ingredients, this recipe for life, is what our scientists are hunting for on other worlds. Exoplanets are the new frontier in the search for life beyond Earth. But the prospect of exploring distant worlds presents an expanding universe of rivers to cross and mountains to climb. How on Earth can we prepare to explore planets we know so little about?
Some of our robots are designed to climb up different surfaces. So we have a claw-inspired robot that uses sharp hooks to grab onto the rough surface, kind of like an insect or a rock climber would scale up a cliff. We also use electrostatics to stick to surfaces. So this is like rubbing the balloon on your head and it sticks to the wall.
One of the key innovations in the new breed of robotics is biomimicry, using biological systems and processes as the model for design. To look for life, behave like life.
We have created a material that has mechanical properties similar to that you see in biological tissues. We have already, with this system, developed swimming robots